Welcome to episode 12 of the Welding Codex. This is a podcast for those who want to learn more about the technical side of welding. We try and talk about welding codes, welding defects, metallurgy, and subjects along those lines. In this episode, welding engineers and CWIs, Peter Kinney and Garry continue the conversation about AWS D1.1 structural welding code, steel. This episode covers Clause 5 and should hopefully finish it up. Which covers fabrication control of distortion and shrinkage, tolerance of joint dimensions, dimensional tolerances of welded structural members, weld profiles, repairs, weld cleaning, caulking, and arc strikes, as well as the tables at the end of the clause. Anyhow, thanks for joining us. Note, Pete and Garry bounce back and forth between code editions 2015 and 2020 during the course of this episode. So we apologize beforehand if the podcast gets a little off track sometimes. Before we get going, a little word from our sponsors. If you're on a budget and looking for an affordable online training course for the AWS Certified Welding Inspector exam, visit train-eng.com, TRAIN-ENG.com, and check out the online courses for Part A, General Knowledge, and Part B, Hands-on Inspection. We also have some buffet-style options for our CWI review courses. If you don't want to take the whole 10-part package, let's say you just need to brush up on metallurgy and weld defects, that's an option. You can pick those. You can pick and choose. You don't have to take the whole course. So we also have options where you can just do questions. I think it's called the Review Question Bonanza. And just hit the practice questions. If you like what we're doing here, feel free to make a PayPal donation on my website, texasweldingengineering.com. Also, check out my YouTube channel for the material that's posted on that platform. Once again, thanks for listening. Welcome to the Welding Codex and our never-ending grind through AWS D1.1. We're still in Clause 5, which is fabrication. So we're going to look at 519, splices. This is where we're going to pick up. Pete, what do you got on splices? I'm going to flick this booger in your direction and see what we got.
Well, basically a splice is where you weld two components together, or maybe a built-up member. So it's, if you need an 80-foot beam, you may not be able to buy an 80-foot beam, but you can probably buy two 40s. So two 40s become an 80. A lot of times, shop splice locations, they're shown on the shop drawings, and you're going to have to have a couple of splices. You're going to have to splice to, if we're talking about like either a built-up eye girder or a rolled beam, you're going to have a splice for the flange. You're going to have a splice for the two flanges and the web, and you can either have them right in parallel, or you can offset them. Plate girders are sometimes done with an offset splice. That can be done. And we got our cyclically loaded, that's where we got to start applying our fatigue requirements. When we have, then the other ones are basically all static.
And with the fatigue stress, that's something that's getting bounced on, or the wind or whatever. So it's a whole nother different category of fabrication, construction, design, whatever. And a lot of that falls into the lap of the engineer and the design engineer. A lot of times on our end, we're not calculating those. We're just following the rules. Oh, this is cyclically loaded. All right, we're going to follow these rules for the splices. So, and it, like one of the things here, 519.2, member splices. Long girders or girder sections may be made by welding subassemblies. Splices between sections of rolled beams or built-up girders shall be made in a single transverse plane when practicable. So it's like Pete said, you got a couple of different variations that you can go on, but generally you try and do it in a single plane if you can pull it off. So
correct. I think with a rolled girder, or rolled beam, it would be a lot more work to make the splices have in multiple locations, where you're splicing the flange here and the web here and the flange somewhere else. That's a lot of work. On a rolled girder, or on a plate girder, it may be easier. But I don't have a whole lot more to say about splices on that one there,
So,
Gary.
all right, let's move on into control of distortion and shrinkage. 520. It's 520 in the 2015 version, and it would be 720 in the 2020 version.
That's
So,
right.
Pete, go ahead with control of distortion and shrinkage.
Well, so the first one the first two are probably the most important. It's sequencing it and coming up with a procedure. So with a lot of things with distortion, welds pull whenever they solidify. The metal becomes, as it goes from a liquid, it expands to a solid, it shrinks and it pulls parts together. So like an easy way is offsetting your part with a little bit of lean to it, and leaning opposite of where you're putting your first bead on. When that first weld bead goes on, it pulls it straight. Welding on one side, then jumping to the other side and welding it. Tacks, putting tack welds all over the place, help to hold the member a little more rigid so it doesn't move. Those are all kind of examples of a kind of procedural, a little sequencing. Sequencing might be is where you build up from parts in a small parts, you make sub-assemblies then because you can balance the weld easily, and then they go into big assemblies. Going around what's called the neutral axis, which I think might be a little difficult to explain without a picture. But the easiest way is if you have a beam or girder that's equal on all sides, right down the middle is the neutral axis. If you weld, the closer you weld to the neutral axis, the less your distortion is. But if we take, let's say, a 10-inch beam that's the same on both sides, and then all of a sudden we put a 1-inch cover plate on it, that neutral axis is now moving up towards that 1-inch plate. So sometimes you got to be careful on that. And if you build sub-assemblies and you kind of trying to keep things around the neutral axis, your overall distortion will be less because there's less pull on it. Here it says contractor responsibility. The contractor is supposed to figure out how they can sequence it and deal with things will shrink. Basically, it's saying you need to know that it will happen. Items where you have a lot of, or shrinkage could be really bad, or distortion, you got to have a written sequence for it. I helped do one of these one time, not on actually on a structure like a building or something. It was actually a rail, like the engine of a rail car, or the front, not just like the piston kind of stuff, but it was the whole frame of the rail car and the body and whatnot. And it was pretty interesting on how to jump around to make all that work. And in piping, kind of get a little off just structural, but it would be applicable, is knowing how much your welds shrink is a good way to know how to help defeat some of the shrinkage, especially if you're tying in between two existing components. Maybe you need to either open that root gap up a little bit more or make that part a little longer to begin with and kind of pry it apart to get it in there, because when you weld it, you're going to have 1/8 of an inch of contraction, and you put a distortion pushing it apart. You welded it, now pulled it together. Welding up wagon wheels is another hard one because everything wants to pull in.
Well, and it gets after, contractor responsibility. The next one is 520.4, weld progression. So if you've got a plan and you don't just weld the hell out of one side and then jump over to the other side and expect everything to be perfect, this is, you've got to have a general plan. Sometimes you backstep weld, you skip weld, depending on what you got going on. You weld on one part and then you come back to another area, or you have welders on different sides of the part welding at the same time. I mean, there's a lot of different strategies you can utilize to defeat, or I guess control, distortion and shrinkage. And a lot of it is skill of the craft. This is things where you got to talk to some dude that's been welding since he was 17 and he knows how these things are going to pull, or, we've got half a dozen, paragraphs here talking about distortion and shrinkage. And there's guys out there that weld these girders that know exactly how they're going to pull, but it's like catching a baseball or something. They just know where that damn thing's going to be. So
Yeah, exactly. Like, I mean, do you offset let's say you're welding up a heavy flange. How many times can you put a bead on one side before you got to sit there and flip it and weld the other side? Or can you prop it up a little bit where when the weld contracts, it'll pull up the tail end? Exactly. A lot of it is just pure experience. The one thing that helped though is back in I think it was in the 60s, Disney made a cartoon about Mr. Shrink. You can find it on YouTube. That'll teach shrinkage stresses and how to deal with them to an elementary kid. Highly recommend seeing it.
yeah, can't go wrong with a cartoon, man. One of the best learning tools I I can soak up information from.
Exactly. The last two in there is minimize restraint. If something's going to move around and be floppy, don't hold it back. Let it move around. That's basically what I guess 525, or in the newer one it's 720.5. And then the last one is temperature limitations. And this is talking about when you got severe shrinkage restraint. And basically, it's once you start welding, keep welding it. Because as soon as sometimes if you get a little bit of weld metal in something, let's say we got a heavy flange or somewhere, I mean, you have multiple things coming in and you get the root bead in, or maybe one or two passes, but your ligament is still really thin comparatively to the heavy sections you're welding. Well, once it cools down, it's going to start seeing a lot of stress, and it may be enough to like basically crack it and pull it apart. So this is basically, once you start, don't stop, weld it up. That's basically what that's saying. And I'm going to say severe shrinkage restraint is not like a common thing you run into every day. Unless that's just your business line, the unweldable kind of things for people. That's an oddity as opposed to every day.
Right. It's like you say, something to keep in mind. And you're going to know if it's a big red flag type of shrinkage restraint or something like that, where it's like, all right, it's not 1 inch welds, it's big stuff, multiple inches, and you just got to go and keep going. So 521, tolerance of joint dimensions. Pete, you got it.
All right. So we got fillet weld assemblies, which is probably, I'm guessing, probably the most common fillet weld, or excuse me, the most common weld we have in the D1.1 world. And what it basically says is this whole section here for materials less than 3 inches in thickness. Our root opening, when you put that one, let's say if it was a plate on top of another plate and you got one standing up vertical, that vertical plate that's going to get fillet welded down to it, you have a maximum, your maximum root opening cannot exceed 3/16. However, it can be a 1/16 of an inch and you don't have to do anything. But if it's above a 1/16 of an inch to 3/16 of an inch, you need to increase it. So if we got a 5/16 fillet welding these two plates together, and you got a 1/16 inch gap, you don't have to do anything. Free pass, click $200. If it's an 1/8 of an inch gap, you need to add an 1/8 of an inch on. So now your 5/16 fillet weld now became a 7/16. If it's 3/16, it would become a half. So it could get real big real fast. When you're dealing with heavy plates or like big jumbo sections that are 3 inches or greater, you get, if you can't get it after straightening or moving things around, you can get 5/16, but you got to put some backing in there. And what I've normally seen for that is subarc flux has been a good one to put in there. Or you can also weld up the backing and basically make it for something that the fillet weld can bite into. Where I've mainly seen this is on big girders where you have plate and the tolerances for A6 allow some waviness, and you got your web going on your flange, and you may need to build up that area to allow to still meet that 5/16 requirement. That's the main thing that addresses right there.
And this is kind of some of the stuff we're talking about here. Is it's a lot more easily explained if we had pictures or cartoons or some kind of diagram and could sit down, but we didn't. This is a podcast, it's all audio, so we really don't have the ability to give you a good picture. So we apologize, but it is what it is. So we're
That's
trying
right.
to explain it the best we can. But anyways, Pete, I think, hit it pretty well there. So I'm not going to chime in and undo his tapestry of quality work there.
All right. Well, the next one is fang surfaces, either 5 or 7, 21.1.1. This is basically saying this is for plug and slot welds. We can still get a freebie of 1/16. When we go above that for these welds, because remember you're transmitting everything through that plug or slot weld area. So keeping things really tight is really important. You need to get approval of the engineer. It's anything above a 16th. If you can't get it into conformance by moving around, swapping end for end, or whatever, you basically got to write it up on this is what the issue is. This is how we feel we want to fix it, and submit it. Filler plates, which would be like if you want to put a little shim in there or something, that's only when it's allowed by the engineer. And you still got to do it in conformance with 4.1.1 in the 2020, and what is that in the 2015 their code there, Gary? The last part, if you're going to use shims, you got to do it in conformance with mine. It's 4.1.1.
211, so that'd be 411.
Yeah, exactly. So basically, you got to come up with a solution, send it to the engineer for approval. Now we're moving on to PJP groove welds, and here we basically can't have more than 3/16, except for here again, 3 inches or greater in thickness. On that one, our magic number of 5/16 comes back. So we do get, leeway, but it's held at 3/16 on PJPs unless you got heavy stuff, and then it's bigger.
And that gets back to the caveat there. If you're going to use 5/16, may be used provided suitable backing is used and the final weld meets the requirements for weld size. So that gets back to using that backing of iron powder or flux or some similar material to weld that up. So you can't just go, hork it in there on a 5/16. You got to have some suitable backing.
Correct. And I've never used iron powder for anything. I have heard some stories of it, but subarc flux is the one I've normally seen used. I think one is it's relatively cheap and easy and readily available.
521.3 butt joint alignment. Parts to be joined at butt joints shall be carefully aligned. Where the parts are effectively restrained against bending due to eccentricity in alignment, the offset from the theoretical alignment shall not exceed 10% of the thickness of the thinner part joined, or an 1/8 inch, whichever is smaller. In correcting misalignment in such cases, the parts shall not be drawn into a greater slope than 1/2 of an inch in 12 inches. Measurement of the offset shall be based upon center line of parts unless otherwise shown on the drawing, which is clear as mud, right?
So exactly.
This is one you're going to have to read a couple of times, and it's basically just gives you, the number on your offset. So 10% of the thickest part, or the thinner 10% of the thickness of the thinner part joined, or an 1/8 of an inch, whichever is smaller. So you're not going to get a hell of a lot of misalignment allowed here. It's either Correct. 10% of that thickness or it's an 1/8 of an inch.
Correct. So what this is, if you got basically, let's say you're welding up two 1-inch plates and you butt them up to each other, you can't exceed 10%, either, a 1/10 of an inch, basically, or a 1/8. An 1/8 is a little bigger than a 1/10 of an inch. So you're going to be held to the 1/10 of an inch. And that is of the two plates meeting up to each other. So, but if we change that to, let's say, we had, for some reason, a 1/4 inch plate tying into that face of that 1 inch plate, 10% of a 1/4 inch is almost nothing. So we don't have a whole lot of alignment to play around with for those not to match up. So we can correct it. It gives us some guidance for how do we correct this, where we can't have a slope so greater than 1/2 inch and 12 inches. So this would be if we were to on that, let's say that 1/4 inch little weld, 1/4 inch plate to the 1 inch thick plate, we can't be adding weld metal that'll produce or have the part bent out of alignment more than 1/2 inch and 12. That's that can get a little difficult. And this is all based on the center line here. We're just using some plate as examples, but if you start to have channels tying in each other or I-beams, offset on that starts to become a little more noticeable, and where you can have issues in tying the two up because now the shapes aren't lining up at all in multiple planes.
Gets back to read it. If you got issues, ask a friend. Draw it out, take a look, number crunching, and
the commentary also. Always look back in the back of the book. There may or may not be commentary for that section. That is something that is a little more unique to the AWS codes, is they have commentary, and a lot of times people's questions are answered very easily just by going to the back and looking up. Not every part of the book has, or every clause has a commentary, but a lot of them do. Now we're going down. What do we got next there, Gary? Groove dimensions?
Grooves dimensions. We got non-tubular cross-section variations with the exclusion of electroslag and electrogas welding, and with the exception of 520, the root opening in excess of those allowed in a figure. The dimensions of the cross-section of the groove weld joints, which vary from those shown on the detailed drawings by more than these tolerances, shall be referred to the engineer for correction. For non-tubular cross-section variations, and this doesn't count electroslag, you go look at this chart, it's going to tell you, all right, this is what's allowable in this figure 5.3. We're going to cover the figures later on in this podcast.
Yes, because they're all shoved in the back of each clause now. It's a little harder to handle both at the same time.
And then we've got 521.4.2 correction, root openings greater than those allowed in 521.4.1, but not greater than twice the thickness of the thinner part, or 3/4 of an inch, whichever is less, may be corrected by welding to acceptable dimensions prior to the joining the parts by welding. So what's that telling us, Pete?
You spread some butter on it.
Yep, you just build it up. You get your good welder, and you get a stack of filler material, and you just build it up and grind it and clean it and follow all the appropriate rules. Keep people in the loop on what you're doing. Build that thing up. Add yourself a little bit of material, clean it up, and go from there.
Correct. And if it's bigger, we got to get the approval of the engineer on that one.
And that all gets back to we talked 5 podcasts ago or whatever, 5 episodes ago or whatever it is. The engineer's got the superpower. If he says you can build it up 3 inches and he's done the calcs, then do it. It's on him. And if he says, nope, I'm not letting you put 1/8 of an inch of material on here, bad juju, bad hoodoo, then that's the end of that too. So a lot of this falls back on the engineer and keeping them in the loop on what you've got going and what direction you're going to go with this. Gouged grooves produced by gouging shall be in substantial conformance with groove profile dimensions. Okay, so that gets us back to these figures. Suitable access to the root shall be maintained.
Yeah. So what this is, when you're now there's multiple methods now of gouging. I mean, before you just had straight up carbon arc, but now you have plasma gouging. Basically, when you're doing gouging, try to make it a nice consistent gouge to allow welding to facilitate the welding of it. That's basically what this is saying, and try to make the gouges similar to those figures. The better you can make your gouging, the less grinding you do, the cheaper it is.
If you're going to remove it, yeah, like you say, kind of keep it to a minimum because that's just time is money on that stuff.
Exactly.
Alignment methods. Members to be welded shall be brought into the correct alignment and held in position by bolts, clamps, wedges, guy lines, struts, and other suitable devices, or by tack welding until welding has been completed. The use of jigs and fixtures is recommended where practicable. Suitable allowances shall be made for warpage and shrinkage. Everything in there, I'm not going to get into it because that's when I used to work out at the Hanford site, it was skill of the craft. It's like me telling coaching basketball and then telling them how to dribble a damn thing. You need to understand this. So there's
Correct.
a lot of this stuff that is just beyond the scope of the inspector or the engineer. It's the skill of the craft. You know how to do this. You need to use your weapons, tools, accoutrements to get that aligned, and I'm not going to walk you through it and babysit you, and unless it just looks like it's an abject disaster, that's on you. So
correct. Yeah, I mean, dogs and wedges. The wind tower industry, we'd use what we call like big spiders to be on the inside to keep the towers round when they're laying on the ground. Building bridges, we'd have these things called girder makers, and we'd squeeze the web and the flange together. So I mean, there's lots of ways to make all this happen, and it is skill of the craft. I like it, Gary.
yeah, that was the card they used to play out there at Hanford. It's like, no, we don't cover this. Skill of the craft. A journeyman iron worker should know how to get us to this point. We shouldn't have to put that into the, write it out and babysit them and chew their food for them. No, this is it. So 522, dimensional tolerances of welded structural members. Okay, we're going to do a fast pass through this, and because a lot of this is just, it would be really difficult to go through all of this. I mean, we can read it, but without having an example or some drawings or, like we said before, some cartoons to work through, it'd just get ugly, us trying to describe a lot of this stuff. And then
correct, it's a lot of measurements, and what I would basically say here is, one is, depending on how valuable what you are building is, you may need to look at, having measuring tapes traceable to NIST, good, or maybe laser measurement devices, or you could be using string lines and tape measures. There's lots of ways to go through this, but it's basically a lot of measurements and then some math associated with it. If you're not too keen on it, find a friend, do it the best you can, submit it up the food chain, and let higher powers start to address it. But it's a lot of this is all done as shop values. If you are building up like the members in the shop, you're doing a pre-erection or whatnot, that's where a lot of this can come into play. Where you can also get bit is if your sub-assemblies or your subparts are all within tolerance, but you have stacking of tolerances, you may be out when you build the whole thing. So that's just some stuff to watch. And I think, what is that, Gary? That applies to, 722 is a long one. So we got a lot of beam and camber. We got sweep, web flatness. We got a couple different web flatnesses, depending on if it's statically loaded or citrally loaded. But these are all kind of where you got to do a lot of measurements and a lot of math. And this is where also it talks about distortion can come and start to bite you on these. One thing that I do want to point out, and it's called, it's going to be 522.6.5 in the old one in the 2015, or 722.6.5 in the 2020, is here it's called architectural consideration. If you're building something that has a lot of exposed steel or members, be real careful and look through the contract documents and the drawings to see if there are different requirements for things that are exposed. In the bridge world, you have what's called fascia girders, and they can have tighter restrictions for the girder right next to it on the inside of the bridge, because people see it, and the driving public doesn't want to see a girder with an oil can dent in it from Distortion. So just be careful on that, because that could be, everything could be within what the rest of the D1.1 says, but then the contract documents has something else that's more restrictive, and now you got to do a lot of heat straightening or something to make it happen, or replace components.
Yeah, and a lot of this stuff, as you transition from, let's say, the craft into, an inspection zone of the universe, into one of those roles as an inspector or a foreman or whatever, and you start dealing with this, it's a lot of reading and understanding and getting into the contract and, playing Scooby-Doo Mystery Hour as you try and ferret out a lot of this information that's going to help you. Okay, I can do this. They'll accept this. Nope, I got to do this, this, this. There's a lot of these things that won't be contained in the code. It'll be contained elsewhere in other documentation where your company said, yeah, we're going to do that, or nope, we're not going to do that. So that's what this is telling us.
Exactly. And the next one, kind of also going through here, we got flange, warped, and tilt. This is for like built-up girders, where the flange either it sucks down and it's kind of droopy on either end, or it's got you welded all of one side, you didn't sequence your welds for one to pull on the other, like you had two welders welding on the same time opposite one another, and you got a tilt to it. So here it gives you guidance on what your offset's allowed to be.
Yeah. And like I said, we're not going to dive too deep into this stuff because it would just be an effort and futility. So,
correct.
Right. Where are we going to now, Pete? We on to Weld Profiles?
Yeah, we could be on Weld Profiles. I think that'd be a good spot.
I think we beat that dead horse enough with the warpage and whatnot. Weld Profiles. Okay. So 523 is Weld Profiles. All welds shall meet the visual acceptance criteria of tables 6.1 and 9.16 and shall be free from cracks, overlaps, and unacceptable profile discontinuities exhibited in figures 5.4, table 5.8, and table 5.9, except as otherwise allowed in 523.1, 23.2, and 23.3. So this is going to kick us into these tables. And here it's telling us, fillet welds, we get, a couple of caveats that tell us what the acceptance criteria are there. 523.2 is telling us exceptions for intermittent fillet welds, because intermittent fillet welds kind of run on a different program. And then 523.3 is groove welds, and that's got a different set of tables. So you want to run with this, Pete? What do you got?
Sure. It's like for the 2020, it's 8.1 and 10.15 for the tables, and figures are all 7, but otherwise all the numbers are the same. We're going the first one we got is fillet welds, and it says the faces of fillets can be slightly convex, flat, or slightly concave. So this can be a big problem. What is slightly? There's ways we measure things, and that's, using our fillet weld gauges, as long as we look like one of the figures in there, and we're allowed by the sizing of any of those tables, 7.8, 7.9, 8.1, 10.15, we're okay. We can have concave fillet welds can be acceptable if we still meet fillet weld size and it's not like a big deep trench. The same thing can be said for slightly convex. Have a little bit of a belly and we still meet our weld size with our leg lengths, that's still fine. But you take any of these to the extreme and we're going to have a problem. The hard part is unless you have some tools to measure it, it's hard to argue what the word slightly means.
Right, and this gets back to common sense and dealing with your inspector and just having been around the skill of the craft. At some point this gives you a general idea, but it also gives the umpire in this situation, the inspector, gives him a little room and discretion to vary the strike zone a little bit. It can't be completely out of control, but different inspectors are going to have different strike zones as far as what they're going to find acceptable. And that's just one of the things you're going to have to deal with in the welding trade. It's not all people are the same, but they should be, operating off the same page for the most part.
Correct. We do get an exception for intermittent fillet welds. The ends of those outside their effective length, the profile requirements are loosened up for those. I think that's mainly geared because if you're putting an intermittent fillet weld on something, you know what? Honestly, it probably doesn't see a whole lot of stress. And that is, I believe, one of the reasons why we get a partial hall pass for what the start and the stop looks like for those.
Yeah, like you say, if you're putting an intermittent fillet weld on there, odds are that it's just holding something in place. It's not the super stressed main beam that's holding everything. The whole thing's going to collapse if this thing doesn't get welded correctly. And not to downplay intermittent fillet welds, but odds are if you're not giving it a full weld, you're just holding that thing together so it doesn't come apart. So did we cover, where did we leave off here?
We got groove welds.
Groove welds.
This is reinforcement. So here it says groove weld reinforcement has to comply with tables 7.8 and 7.9, and it has some provisions below. And here it says welds shall have this is another kind of, feely word, is a gradual transition to the plane of the base metal surface. Well, we don't have a value for that. It doesn't say. All it says is our weld can't have reinforcement that exceeds a value from those tables, and a gradual transition. So, and this is common in American codes where we have we mandate a maximum reinforcement height, but we don't have the entrant angle between the base metal and the toe of the weld. There are some European standards that actually do that. The more the obtuse the angle, the bigger the angle, or the more shallow approach, they call it a class, like a class 90 or a class 100 would be for fatigue sensitive items. And I remember dealing with wind towers, and it was, what's a class 90 wind tower? Well, we had a rude awakening of what a class 90 wind tower was. It was until we got better on how making the welds in the weld profile improved, there was a lot of grinding, and that was trial by fire on that one. But so we have moving down, we got some flush surfaces. So now flush doesn't mean grind the heck of the base metal. That is one thing flush does not mean. But we need to grind the reinforcement from the weld to be flush to it by no more than 30 seconds in height, and blend smoothly. To me, blend smoothly, gradual transition, that's kind of a skill of the craft. For most applications, moving into some more oddball items or cyclically loaded things, that's where you may need to start having a little more procedures, whatnot, to where it can be handled effectively, especially without rework.
Well, and I'm going to jump in here on gradual transition. It's like one of those Supreme Court cases back in the day where the guy, they were trying to, I think it was with Jerry Falwell and Larry Flint over Hustler or whatever, and the guy said something to the effect, one of the Supreme Court guys said that I don't have a definition of pornography, but I know it when I see it. And gradual transition to me kind of falls into that category. I don't really have a quantifiable empirical definition of what gradual transition is, but I know it when I see it, and I know it when I don't see it. So that's kind of what with gradual transition. It gets back to skill of the craft, and then also skill of the inspector to be able to look at it and say, no, dude, that's not gradual transition. That's not, you didn't even get it. You didn't even get the ball over the plate. You hit the freaking mascot with the ball. You know what I mean?
Exactly. And a lot of time where you have flush surfaces, there are some other high fatigue kind of things, but a lot of time it's flush is because some other component might sit there where you have a welded case or a box or something, and another component has to live there. So let's say like a pump or something has to bolt down, and if you try bolting down this cast iron pump and you got a big weld bead running right down the center, when you suck down those 4 bolts on each ear, you're going to crack an ear off or something. So that's like an example where like a flush surface would be. That's a good example. And finish methods and values, that's 723.3.2. That would go if you're grinding or you're sanding or prepping the surface, not just for flush surfaces, but this would be more for appearance or specific function. Fatigue is what I mainly have dealt with, where building subsea pipelines, we had to hit different fatigue curves, and basically we got it we had finish values we had to hit, and we would use different grits depending on what value we needed here.
Like it says in here, grinding or machining, generally if you're going to machine something, you have a specific target that you're trying to hit. So, it's giving you some numbers there for, 250 micro inches or 125 micro inches. It's giving you a target. So this is a very specific target you're trying to hit for very specific situations.
Correct. And the way I've measured these a couple ways. One of them is a little more subjective. You can get these little plates that are different roughness values by different processes, and you basically put your finger on them and you feel it, and you go and you feel the part, and you go back and it's kind of subjective. You're not testing a big portion of it. They do make little machines that also go through, and they will also look at the value of it as well. RMS is a common value. That's some value in RMS is what's used to measure roughness. I've done both. There's a time and place for both. It can be a little painful, and you will learn a lot about different abrasives when you're trying to go down this road for meeting these requirements effectively. Shelf bars, that's basically when you got to weld primarily in the 2G position, and you got something you're welding on, and it's basically catching the bottom half of your, it's right below the bottom weld toe, and that's what it's for. Here it's basically saying they can only be left for statically loaded members. If you have that on something cyclical, that's basically just made a perfect crack zone for it.
Technique for plug and slot welds. Okay, plug welds. The technique used to make plug welds when using SMAW, GMAW, except for GMAWS and FCAW, shall be as follows. So it goes in and gives you, for flat welds, it's going to tell you exactly how to do it, the motion you're going to follow, the arc shall be moved to the periphery of the hole, blah, 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 blah. So it tells you how to do these for flat, vertical position, overhead position, and it also gives you the instructions for slot welds. I'm not going to read through all these. Do you have anything you need to throw in here, Pete?
I would just say, before you say, I can just read this once and go do it, practice. Make a couple of these. You'll be surprised what happens when you cut them on a bandsaw, and you'll see what you see. So while this is good instructions to follow, practicing in actual underneath the hood, making this happen will make these instructions make sense. And one thing, though not for plug and slot welds, it does tie in perfectly to our next section, though, is repairs, is misplaced holes. People want to repair misplaced holes just like a plug and slot weld. While that may or may not be possible, we'll get into that in detail in a little bit.
525 repairs. The removal of weld metal or portions of the base metal may be done by machining, grinding, chipping, or gouging. It shall be done in such a manner that the adjacent weld metal or base metal is not nicked or gouged. Oxygen gouging shall only be permitted for use on as-rolled steels. Unacceptable portions of the weld shall be removed without substantial removal of the base metal. The surfaces shall be cleaned thoroughly before welding. The weld metal shall be deposited to compensate for any deficiency in size. So that's just basically telling you if there's something that needs to be fixed, then you got to chip it out of there, chew it out of there, remove it by whatever method is acceptable to your contract and or engineer or your company's quality plan, and then you clean it up and put it back in there, and you try not to remove as much of the base metal as possible.
Correct. And this thing about the oxygen gouging is hot, really hot. It's fast. It's super fast because it's so hot. And when you have any material besides as rolled steels, the heat can start to affect things, and that's kind of the basis for this limitation here. So there is a rationale for it, which I can stomach. Thou shalt not kind of rules better when I understand what'll happen if I break them, and that's kind of the reasoning for there. And like you said, Gary, however you want to remove it, for the most part, is up to you. And that's basically what the contractor option basically talks about, is removing it, replacing it. And if you do repair it, here we have rules about how much or what we have to fix here. So if we have excess convexity, reinforcement, overlap, it has to get removed. There's a lot of ways to do it. Depending on how bad it is and how big of a weld it is, normally it comes down to big grinders. I do know a friend of mine worked at a company, and this excess convexity or excess reinforcement, they had a much tighter tolerance than what D1.1 ran. And the reason they did it is because they didn't want people to make oversized welds and cost more money. So they always made the welder always grind everything down tighter. But that's, I guess, another way to learn how to make sure you got your welds the right size. The same thing with excess concavity or craters or undersized welds or undercutting. Basically, if you have a hole, the only way you can make it better is you've got to fill it back up. So you got to add additional weld metal to that.
I was going to say, though, under contractor's options, one of the key things there is the repaired or replaced weld shall be retested by the method originally used, and the same technique and quality acceptance criteria shall be applied. So that's what's telling us is if you found a defect with an x-ray and then you chewed it out of there, you can't come back and then just say, well, we're going to visually and mag particle this and call it good. No, if you found the defect with ultrasonic, you got to fix it and then retest it with the ultrasonic and the same acceptance criteria. You can't switch games. You can't switch criteria in the middle of the game here. So that's just one of the things you need to understand about that. That's whatever test method, non-destructive test method you use to find the defect, you got to retest with that after you fixed it. So
that's a good point, Gary. I completely missed that. I'm glad you brought that up. Yeah. So if we found it through, any the only mandated inspection in the code is visual. With everything else is mandated by contract. And so yeah, you're right. If the contract says you got to inspect it by whatever method, and you found it, you got to repair it by that and re-inspect it. Good catch there, Gary.
Yeah, and then we've got cracks in weld or base metals. The extent of the crack shall be ascertained by the use of acid etching, MT, or other equally positive means. The crack in the sound metal to 2 inches beyond the end of the crack shall be removed and re-welded. So that tells you how to chase cracks in the weld or the base metal. So you can't just go to the end of the crack and call it good. You got to chew out a significant amount of material after the end of the crack. And this is put in there because this code's been around for a number of years, and this is practical experience. And I'm sure somebody's got mathematics to back this little caveat up. But if you're chasing cracks, you got to go 2 inches beyond.
Correct. Yeah, because what could also happen is the crack can become really fine and you can no longer see it. That's also some of the guidance on it.
Yeah, and then let's see, localized heat repair temperature limitations. Members distort. This is 525.2. Members distorted by welding shall be straightened by mechanical means or application of a limited amount of localized heat. The temperature of heated areas as measured by approved methods shall not exceed 1100 for quenched and tempered steel, nor 1200 for other steels. The part to be heated for straightening shall be substantially free of stress and other external forces except those stresses resulting from mechanical straightening. So this is just giving you a target here. If you're quenched and tempered steels, you don't want to get above 1100 degrees, and then you don't want to get above 1200 degrees F for other materials, because those are 2 temperatures where, without getting too heavily into metallurgy, you get above those temperatures and the game changes on stresses and what you're doing to the material and softening it. And I mean, we could have 15 hours worth of talks on what happens metallurgically with steels when you punch through 11 and 1200 degrees.
Correct. And another one I'd throw in there that you may not think about as for quench and tempered is your TMPC steels. I'd be careful about heating those up real hot as well. And this is also one guidance put on this is if you can do this somewhere where it's a little dark and a little shady, it's a lot easier to tell when you're getting stuff hot than if you're out in the sun. Red hot steel is hard to read color in the sun.
Yeah. You have a chance of severely impacting the microstructure and the mechanical properties of the material if you're trying to do this out in the hot sun and trying to find that sweet spot in regards to the color.
Correct. Lots of temp sticks.
Yeah. 523 or 525.3, excuse me. Engineer's approval. Prior approval of the engineer shall be obtained for repairs to base metal other than those required by 514. Repair of major or delayed cracks, repairs, but to ESW and electro gas welding with internal defects or for a revised design to compensate for deficiencies, the engineer shall be notified before weld members are cut apart. So you got to go talk to the engineer on some of this stuff. If it's just an absolute abject disaster and a mess, get the engineer involved and let him know, especially if you're repairing electro slag and electro gas welding. Before you start chopping in there, let him know what you're doing and get a plan.
So I want to say with the first couple months after I got out of school, this last sentence, the engineer shall be notified before welded members are cut apart. And there was a shop that they had a train wreck, and they basically had an 8-foot weld that was horrendous. And the plate was long, so they basically said, we're just going to flip these end for end. And a young, very green engineer was like, oh, you need to submit a whole plan for this, blah, 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 blah. My boss, the engineering manager, was like, no, just cut it apart and flip it end for end, and we could care less. So that was something kind of a learned thing, is sometimes, even though the code definitely says it right here, we may need to kind of use some common sense on that.
I was going to say, too, in regards to repairs, I worked for a place when I was out in Washington. We did a bunch of work for the federal government, getting rid of chemical demilitarization, like, nerve gas, nerve agent. We made machines and tanks and this whole system for getting rid of those. Anyways, this outfit, they had a log, and it was I was the welding engineer, and we had a log, and it was the repair log. So anytime we'd repair welds on this stuff, I'd go out, take a look at it, look at the failed x-ray. We had an level 3 NDE guy who would say, yep, it's failed. And I'd be like, all right, we got to fix it. It's not his job to tell him how to fix it. That was my job. So anyways, I had a log of all the repairs. So then you could keep track of, that repair got closed, and we had a process for, I'd tell them, okay, you're going to grind out from here to here. You're going to do this, 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 and this. And we had a little repair plan so that we could, track it. Oh, that repair never got done. all right, or what happened to that repair? You guys never gave me the paperwork back on that. And it doesn't have to be anything elaborate, but a lot of times it's just a sheet and a Excel spreadsheet and a Word document. And you got 10 or 12 lines on the Word document explaining, okay, where the repair is, what you're going to do, blah, blah, blah. And you give it a number, and there you go. And especially if you're doing a large volume of work through a shop, a lot of times, doing a little extra bookkeeping and on stuff like this can save you a lot of trouble later on. So anyways, thoughts from the peanut gallery.
Yep, no, I agree. We did the same thing on pipelines, where repairs were at, who did what, when it occurred. I definitely agree.
Inaccessibility of unacceptable welds. If after an unacceptable weld has been made, work performed, which is rendered that inaccessible or has created a new condition that make the correction of the unacceptable weld dangerous or ineffectual, then the original condition shall be restored by removing the welds and members or both before the corrections are made. If this is not done, the deficiency shall be compensated for by additional work performed conforming to an approved revised design.
What this basically says is this is going to cost you a lot of money and a lot of time. If making things in subassemblies is great, however, you need to have each subassembly signed off for, inspected, blessed, whatever it needs to happen before it goes into the next part, where all of a sudden you have like 20 things welded up, and for some reason some weld is unacceptable for whatever reason, and now you got to start cutting a bunch of stuff apart to get to it to repair it. That can a lot of time, a lot of money associated with that. So try not to put yourself in that situation.
Yeah, and if you can't get in there, it's telling you it's got to be compensated by additional work, whatever that entails, or a revised design. So that sounds like a lot more money and time and effort. So like he's saying, don't put yourself in that situation. Okay, here we go. Welded restoration of base metal with mislocated holes. 525.5 and 725.5 in the 2020 version.
All right. So we started to touch on this earlier for plug-in slots, but here this is for mislocated holes. Basically what that is, you drilled a hole in the wrong spot. There was an up and a down, and somehow you got the down and the up confused, or the right and the left, and you punched a hole in the wrong place. How do you fix it? A lot of times it can just be left open, or you put a bolt and you tighten it up. What the bolt does is it produces a compressive stress around the hole. Sometimes it's all you need. There are other times when you got to weld it up. And on welding it up, we could have a couple different reasons why we need to have it welded up. One could be appearance. There's no structural benefit. It could be fine if it was an open hole, but I just don't want a hole there. Or maybe it's corrosion or a non-structural reason. A lot of people will use the plug welding method because it's cheap and it's fast to weld up the hole. However, what you don't do is you don't get a through thickness strength from it, or in your tensile usually across the weld isn't as great as the original base material. So there's sometimes when a plug and slot kind of repair is unacceptable as a welded repair, and that'll come in when we need to have in tension zones, is where all of a sudden we got to start doing a lot of times what they call like a boat repair, where you weld up half of it, you put a plug in, you weld up half of it, then you go and you gouge out the other half and you weld it back up, and you have an elongated boat that's in the direction of tension. It takes a lot of time on a thick flange, but it's the way to get full guaranteed strength back. And through here, the engineer has to approve the plan. You have to WPS. You got to do the NDT to approve the material was good. A lot of times could be UT, RT, followed by something beyond visual as your surface NDE. And then if we throw another wrench in there where we got quenched and tempered, there's other mainly heat input which rolls into our WPS, or maybe even pulsable heat treat has to get thrown in there. So depending on what kind of structure you're building or what kind of widget, and depending on where this hole is, this hole could be a major hole of time and money, or it could be simple as, I could care less, there's another hole there, doesn't do anything. But whenever you have one, you need to get the engineer to approve what you are doing with it. That's critical. And here we even have, for quench and temper materials, we have tested what you have to do, and we do some side bends, some Sharpies, or reduce section. Like I said, all of a sudden this hole, because we didn't measure twice or look at the print and we did something from memory, this is now like a $5,000 endeavor. So a simple hole can become a huge vacuum of time and money.
Oh yeah, and especially when you start, throwing in post-weld heat treatment or Sharpies and all this stuff, and then engineering time. You definitely do not want your engineer, or if you got to get an engineer from out of the company, you don't want me billing against your job, me and Pete, if we're in the company, because our billing rate is going to chew up your costs on that job in a big, big way. So like Pete said, this drilling a hole in the wrong spot on this stuff, it goes from being, oops, that's not a $10 fix. That's $5,000-$10,000, depending on how ugly it gets, how much you got to argue with the client, how much, it can just spiral out of control. So like you said, measure twice or three times and on the holes, and make sure you get them in the right spot. So ugly. Let's talk about peening, Pete. 526. I've never dealt with.
So peening I've dealt with a couple times. It was twofold. One was on cast iron stuff, which is a different rodeo completely. The other one was called ultrasonic peening, which is a little different, and we'll cover that. I'll tell you that story in a minute. But basically, peening puts a compressive stress into the surface of the weld. It could also be it doesn't have to be like it could also be as you're welding, you peen to relieve stress. Now in the code, it basically says you can't do it on the root pass or on the surface layer, or the base metal at the edges of the weld, except it does have some guidance in there for tubulars. All right. The reason for not doing it on the root is if you're whacking it and you're hitting it with a good hammer or chisel, you could crack the root because it's not, the ligament is pretty thin. You get the root in, you get a hot pass. All right, now we're starting to have some metal in there you can start whacking on. And the reason you don't do it on the cap is that's your final, and you're mainly doing visual, or even if you're doing mag or something else, it can obscure cracks. So that's the two reasons why we can't do it on the root and the cap. Edges of the base metal is kind of the same reason of hiding cracks, except as what 1023 or 102363 is. So that's why we can't do it. And when you're using just normal chipping hammers and chisels, or your normal needle scaler, that's not doing peening. Peening is whenever you actually see like, wow, that's like a dent. I mean, that's like you grab a ball peen hammer and you start whacking on things. That's going to be considered peening. The times I ran also, and the other one was ultrasonic peening, and you would do this. It was a big tool, kind of somewhat looked like a small jackhammer, and instead of pounding you to death, it had this little head that moved at an ultrasonic. So it was super fast, and you would do it at the toes of the welds to increase the fatigue category, because you're putting a compressive stress in and preventing cracks from starting to grow. And it is used. It's used on mainly cyclical structures, on more of a rehab type scenario, where you want to extend the fatigue life on something, or some heavy equipment. They use it. I mean, think big like earth movers and stuff. Just one thing you don't want to do is put a bunch of time and money into doing peening on things and then go and hot dip galvanize it, because that that temperature and that hot dip galvanizing will kind of do a stress relief on you and kind of lose your compressive stress that you spent a lot of time putting into it. So that's all about I have to say about peening there.
All right, and then we move from peening to caulking. Caulking shall be defined as plastic deformation of weld and base metal surfaces by mechanical means to seal or obscure discontinuities. Caulking shall be prohibited for base metals with minimum specified yield strength greater than 50 ksi. I've never dealt with caulking either.
No, I haven't either. I mean, it's something kind of like peening as well, but it's yeah, I've never dealt with it, and it's also, I mean, basically as we've seen, it's prohibited. I don't have a whole lot of to say about it, but I guess if you're going to do it, you better figure it out because there's a whole lot of reasons on why you got to make sure all your inspections are done, which isn't a big deal. But if you're sitting there deforming the surface, extreme deformation of the surface, you're increasing your surface area and you're making a lot of sharp ridges for coating failures. So the coating might not grab onto it real well. And here it is. We got to have it improved by the engineer. So I'm sure there's a time and a place for caulking. Like I said, like you, I've personally never dealt with it.
Okay, so which brings us to arc strikes, 5.28 arc strikes. Arc strikes outside the area of permanent welds should be avoided on any base metal. Cracks or blemishes caused by arc strikes shall be ground to a smooth contour and checked to ensure soundness. And arc strikes are a big one in any code, not just D1.1. That you don't want to be striking an arc outside the weld zone because it can lead to stress concentrations and failures later on, because the problem here is that you take a piece of material and you heat it up and basically quench it. So you have this martensitic structure in this material, and it's just this place where it's just going to fester and it can cause a crack, and depending on the cyclical nature of the loading situation, you can just have all kinds of bad things going on. So that's why it's telling you, you got to grind it smooth, take that martensitic, the martensite isn't going to go very deep into the structure. So you just got to kind of scuff it off, take it down, a little bit, take some meat off, and then have it checked with dye penetrant and visual, and have somebody, an authority, take a look at it and make sure everything's good to go. Thoughts?
So the pipeline world, this was extremely painful. An arc strike could drive a cutout. And it wasn't just an arc strike from the electrode. You could have an arc strike from a ground clamp. So what we would do is we would basically grind, or I'm saying grind, but it was more like of sanding out the indication. Then we would normally check it by acid etch to make sure that it etched completely the same. That means you've got the heat affected zone gone, or the martensitic area. And then it was either a wet mag or magnetic particle tested. Dye pen could also work. And then we had thickness checks on top of that, because you were making the wall thickness thinner and you had a level that you couldn't go below. So arc strikes can be serious business depending on what industry you're in. Here it's basically grind it smooth, make it disappear, and ensure weld soundness. It's sound. Pretty simple. But I wouldn't hold it just to arcs where you're all of a sudden you got the stinger out and you smack something. I'd also check your ground clamps as well. That can be another part where you can also get an arc strike occur.
Yeah, and you just got to keep track of this and make sure what materials you're working on, the industry. I worked in a foundry up in the Northwest, and we did some HY80 and HY100 material, which is like submarine hull material, more or less. And anyways, whenever we'd cast something out of that, there was very specific rules on how you had to weld this stuff up and remove it and grind it back flush. And, it was basically you had to put in a temper bead to deal with the arc strike. So just be cognizant of what you're welding on and the code and the code requirements and your company requirements on arc strikes, because it's a very serious thing, especially like Pete was saying in the pipeline industry. An arc strike or even a dent from a backhoe in one of those pipelines, man, you might not think it's going to be anything now, but 2 years from now, after that thing's had a chance to gyrate a little in the cyclical nature, you'll have an explosion or something just go very wrong. That's why they don't allow arc strikes. That's why arc strikes are such a big thing. Throttled that 5 lines or 4 lines of material pretty.
That's right. Now we got weld cleaning there. We got in-process cleaning. In-process cleaning is basically, as you're welding, how do you clean this? And it basically says remove the slag. All of it has to be removed by brushing or other suitable means. It doesn't exactly tell us how we have to do it, just make it happen. You could use a needle gun, you could use a chip and hammer, you could use a wire brush, you could use a grinding wheel, you could use your buddy's thumb. I mean, anything to basically get it clean between every pass.
Yeah, and this goes back to skill of the craft and being a grown up and, realizing what the hell you got to do to produce a sound weld. You can't be leaving slag and dirt and paint and crud in the weld or other deleterious material. So you gotta remove all that stuff before you strike the next arc and start depositing the next layer of weld metal.
Correct.
Cleaning of completed welds. Slag shall be removed from all completed welds, and the weld and the adjacent base metal shall be cleaned by brushing or other suitable means. Tightly adherent spatter remaining after the cleaning operations is acceptable, unless it is removed is required for the purpose of NDE. Weld joints shall not be painted until after the welding has been completed and the weld has been accepted. So that's just common courtesy to the weld inspector. Hey, knock all the slag and crud off, because he's not going to look at it until you get it cleaned up enough to look at. And if there's spatter and you're going to ultrasound it, you got to bring all that spatter, take all the spatter off. But it gets back to just putting out a quality product,
Correct. I've always found humor when it's like, hey, we need to inspect these welds. Well, they're already painted. Well, does that mean we don't need to inspect them anymore? I always kind of thought that was a lame cop-out excuse. Weld tabs.
Okay, weld tabs, 530.1, use of weld tabs. Welds shall be terminated at the end of the joint in a manner that will ensure sound welds. Whenever necessary, this shall be done by the use of weld tabs aligned in such a manner to provide an extension of the joint penetration. So weld tabs, what we're talking about is you have an extra inch or two, you throw a little piece of material that is probably similar to what your base material is, but it gives you a start, so you don't actually start and or stop in the weld joint. You've got a little extra time there to get it going, and then you're in the weld joint, and then when you're terminating the weld, you go an inch or so after the weld, and then you can come back later on and knock those weld tabs off, clean everything up, and life's good. So you know that if you had any crater cracking or any kind of crud in either the start or the finish of the weld, you've got it outside of your weld. So a lot of times you'll have porosity with 70-18, on the start. It might not be a significant amount of porosity, but sometimes you'll just get a little bit of porosity on that start and let's say a crater crack on the end. So a lot of times a weld tab is, convenient for that. What do you think, Pete?
I think they're great training wheels. They work great. I highly recommend them. It allows the arc to, multiple processes, the arc to stabilize, and you can start traveling, whether it be sub-arc or you're right with, a lot of stick electrodes, they want to stabilize. And you're right how the one thing you have to watch out for is stacking of indications, where if your starts are always on top of one another, well, each little bit wasn't bad by itself, but all of a sudden you got 10 of them on there. Now you got a big lob of porosity. So they're simple little things. They make life easy. Highly recommend them. And what it's then the next one, where after the use of them, the removal, it says For non-tubular structures, they don't need to be removed unless required by the engineer. I don't know a whole lot of places where you could really like leave them. I'm assuming there are places where they would be acceptable. Normally, I've seen them removed on anything I've built, because one is you got this little chunk of metal hanging out there that's definitely going to grab onto someone if anything. But basically, then the next section is for cyclically, and they have to be removed and basically make the ends nice and smooth. So then the one after that is make them pretty, and you have to leave a little bit of reinforcement, but not to exceed 1/8 of an inch. And you have to have a faired and a slope of 1 in 10. Slope in 1 in 10 would be, it could be for any measurement system, but basically 1 inch in 10 inches or 1 micron in 10 microns. It's basically the definition of a slope, and it's unitless because it just uses the same units. Not sure what to really add to that there, Gary. What do you think?
No, I think you pretty much hit it on there. And a lot of this gets back to with weld tabs being grown-ups. Making it look nice, putting that garnish on the, the whatever, the chicken cacciatore that you're bringing out of the oven. I don't know. Draw whatever conclusions you want, or use whatever metaphor you want to use. Yeah, it's a lot of it's just being an adult and trying to put together a quality product. And tabs, like it says, removal weld tabs for statically loaded. It's not the end of the world, but it looks better. Somebody's like, why is that tab there? What's that little piece of metal sticking out? It doesn't take that long to knock these things off, grind them, get the apprentice over there with the really big grinder and give him a little grinder time cleaning this mess up.
Oh, exactly.
Okay, so that wraps up Clause 5 in 2015 or Clause 7 in 2020 fabrication. But we're going to dive into a little bit. We're going to cover some tables, 2 or 3 of these tables that are significant. Table 5.1 is allowable atmospheric exposure of low hydrogen. In our, I think it was our first podcast or our first episode in fabrication, we talked about allowable hydrogen and low hydrogen electrodes, etc. So here you've got SFA 5.1 and then you've got SFA 5.5. So there's a couple of different things you need to look at. You just need to make sure that you're using the right table with the right welding wire or stick electrodes, what you need to do. And some of this stuff, you've got a half an hour. Like if you're using like an E118, you can only have that stuff out of the oven for half an hour max, or over half an hour to 4 hour max. You just need to read this chart and make sure what you're working with, and stick to it and have a plan. And anything you want to throw in there, Pete?
Well, so the pressure vessel guys will understand when you said SFA A51, that's the pressure vessel world uses a slight modification of the name, but it's otherwise the same as A51 or A55. But yeah, as Gary said, have a plan. Don't give a guy a 50-pound box if he can only burn, 10 rods, 20 rods an hour, because you're going to run into a problem. Give people smaller quantities, or give them heated quivers where it's easy. Then some of the stuff you don't even have to worry about anymore. But know your maximums, know your amount of times you can rebake, or just the other option is all this stuff gets thrown into a bin for non-code use, which can be its own problem child in the future.
Yeah. Minimum holding times, table 5.2. You can read through that.
So yeah, yes, table 7.2 or 5.2 and 5.3, 7.3. This is all dealing with heat treatment, where this is how long you hold something based on its thickness, and then there's alternative temperatures, which basically means if you're not cooking it for as hot as it's supposed to be, you can decrease the amount of temperature, but now you need to hold it for longer periods of time. This is not common in the D1 world or D1.1 world, so that's just what those tables are. I think we're on 5.4 or 7.4 for repair of mildew. So this is actually one, if you're dealing with especially once you start to get into heavier materials, and I'll say heavier is probably normally about over 1 inch, is you'll start to see more discontinuities in the steel. I mean, we think of steel being as homogeneous, there's no problems with it. It's not like lumber where you got knots and stuff. Well, once you start getting thick, you do start to have knots or magnesium sulfide or manganese sulfide inclusions where it's not normal, or you have like some fins and tears. And this table basically tells you how much of it can you fix before you got to run it up the flagpole and get engineer's approval, or do you have to repair it? So here, like if it's a very small discontinuity, you don't even need to do anything. But this table basically gives you that guidance.
And then we're going to go to table 5.5, 5.6, and 5.7. 5.5 and 5.6 are camber tolerances. We discussed that. It's some math. It'll give you the numbers there. 5.7 is the minimum fillet weld sizes. You can read through that, for base metal thicknesses.
Correct. And what I'd say on table 7.7, this is kind of where the big letters giveth and the little letters taketh. So really read your footnotes on here, and there are some wiggle scenarios. So like where you have a minimum fillet weld size. Well, if you have a 1-inch thick plate and you're welding on there something thin, well, there's no point in really making a weld exceed the thickness of the thinner part. That's kind of dumb, unless there's some really valid reason for it. But make sure you look at your footnotes on this one, and because it throws in there like cyclically loaded structures as a footnote that is different than your statically loaded. That's all I really have on table 7.7.
Yeah, it's pretty self-explanatory. Read it. Okay, 5.8 is Weld Profiles. 5.9 is Weld Profiles. And this is going to tie into, as we jump down to figures 5.4, I'm going to skip over some of this. 5.2 and 5.3 workmanship tolerances. You want to go into that, Pete? Are we good?
I think, like I said, on those, look at the footnotes. Make sure that it's not taking or giving you something, and it's pretty self-explanatory what you can get in here for tolerances. And if you're basically following the recommended joint designs in the book, they'll kind of have these already incorporated into them.
All right, so if we go down to figure 5.4, this is where we're getting into the requirements of the weld profiles. So there's a whole slew of these in here, different weld profiles, and it's telling you, okay, this one's good, this one's bad, acceptable, unacceptable, desirable. It's telling you what you're looking for. If almost any code you look in, it's going to have this in there or something similar. Whether it's a military code or whatever, it gives you a general idea. Okay, if you got it all humped up like this is bad. Oh, the weld I have looks something like this and we can measure it. All right, this is pretty good. Or we didn't fill up the weld good enough. This is bad. So that's what table or figure 5.4 is giving you. And it gives you some information on weld profiles for fillets and different joint configurations.
Correct. And so when we look at our table 7.8, we find what kind of weld type we have, and then it correlates with the joint type, if we have a butt or a corner or an inside and outside, a lap or whatever. And it gives us a schedule, and then we come down to that schedule, and that schedule, like let's take for example, a corner joint on a groove weld, so that's schedule B. We come down and we figure out our thickness of our plate, and that'll tell us what our minimum, our reinforcement or mins and maxes are, and also what our convexity or concavity maximum is as well. So that's how we use these. You have to use these two tables in concert, and then you look at the figure to get a graphical representation of what your tolerances are. And I think that basically covers, I think, the figures in those tables, doesn't it, there, Gary?
Yep. That wraps up our adventures in Clause 5, Fabrication, for the 2015 version of the code, or Clause 7 for the 2020 version of the code. We'll move on in the next episode to Clause 6, Inspection. Thanks for listening. Hope this podcast was worth listening to. We're going to have more content coming out. Also, if you want to shoot me an email, gpacex@gmail.com. Give me some ideas, or maybe there's some questions that you'd like me and Pete or me and Joel to answer in regards to welding codes, filler material, or any other material joining question that you might think we have a shot in hell of answering. Anyways, thanks for listening. Take care. Peace out.